Hello, we are the MedTuned AI team. Thanks for coming to our presentation today. So my name is Dana, I'm a fourth year medical student.
My name is Mehek, I've just graduated.
My name is Rashida, I've just finished honours.
My name's Bruno and I've just finished year 2.
Yep, so our team name is actually related to our research purpose itself. So when we said med, it means synthetic data generation using clinical cases. And when we say tuned, we meant fine-tune AI model to enhance clinical reasoning. And all our projects is based on artificial intelligence. That's why we named ourselves MedTuned AI. So for our research project, we basically had 2 research questions that we want to answer. The first one is, does fine-tuning improve the clinical reasoning of the llama model compared to its non-fine-tuned version? And the second one is, which method produces better clinical reasoning, fine-tuning the model or utilizing a prompt? So this sounds very complicated at the moment, so we'll break down later on, but these are the 2 research questions that we're going to focus for our project today. Just to give a basic information of what synthetic data and llama is. So synthetic data is artificially generated information replicating real-world data, and its importance is increasing within the medical field because there is insufficient patient data in the real-world medical databases. So in order to fill in the gaps, we're generating a lot of synthetic data. Llama is an open source large language model developed by Meta AI, and it allows us to fine-tune the model according to our needs. So that's why we chose llama as a model to fine-tune. So basically for our project, we use synthetic data and llama model to give inputs such as patient history, physical examination findings, and investigation results, and provide a diagnosis, management plan, and the detailed clinical reasoning. So we're going to dive into our research project now.
Yeah, so in terms of our project timeline, we started off with project brainstorming, so we came up with a few ideas and concepts we were interested in. Based off that, we used our initial llama model, which was the large language model, and then we fine-tuned it to produce our final model. So in terms of fine-tuning, what we did was we produced human seeds, which I'll go on to a bit more later, and we used that to generate thousands of synthetic data, which then was used to fine-tune our final model and then evaluate that as well. So going on to explain human seeds, so what I mean by human seeds is in this case, we produced 9 clinical cases, so produced by us, and these are cases which had the structure of, as you can see here, inputs and outputs. In terms of inputs, we had things like patient history, information, examination, and the investigation findings. And outputs were things like differential diagnoses, and we followed a structure like Vindicate, for example, to make sure we covered a broad differential list. And then we also had clinical reasoning. So the aim was to put the input into the model and then get an output based on that and see how it improved. Next slide, please. So based on the 9 human seeds we made, we then produced about 42 more from ChatGPT, and we refined and edited those as well. And in total, we had 51 seeds. Just to note that when we were producing these seeds from ChatGPT, we used a relatively high top P and temperature, which makes it a bit more creative in terms of the differentials it produces. And that finally produced the 51 seeds we then used to produce synthetic data.
So then I used those 51 very high quality human generated seeds to produce the synthetic cases, and ended up with 2,500 standard cases and then 1,200 rare cases. And then after those were refined, we had 2,700 cases left for fine tuning. So for the standard cases, these are like, when I say standard, I mean that I didn't specify what disease I'd like them to make a case about. So it was used Gemini 2.0 Flash Experimental, which is like quite a convoluted model name, but it's one of the top rated Google AI models to generate those new standard cases. So I would give the prompt something like generate a new synthetic clinical case data based on the examples, and then loop through each of the seeds and then ask it to generate a new clinical case. And I would loop through that for every prompt. So every prompt was including all 51 of those high quality cases. And then those would get saved to a CSV file, and you can see like a little code snippet in the bottom. That's an example. We'll provide the slides if you want to read through it. Sorry. Then for the rare, online I found a database of 21,000 rare diseases. You can see that's the start of it over there. And then for those rare diseases, that was the similar prompt to before, but I would specify which disease I wanted it to generate. And due to time constraints, I only selected every 21, rather than just doing the first 1,000. Every 21 ensured that it wasn't like having too many diseases that are similar because they're in alphabetical order. Like you can see they're all quite similar issues there. And then also being careful, if you'd like to do this for yourself, be careful with incorporating a time delay between API calls because you can quite easily overload the model. That's another example of what it produced. And then with those, I employed cosine similarity as a spike qua to ensure that there weren't too many of the same cases replicated. Because just from a brief inspection, there was lots of AMI as an example. And then that ended up removing over 1,000 cases, which was kind of disappointing, but good for the high quality. And then the threshold for that cosine similarity was 0.9. And you can see some snippets there of first the one on the far side is the cosine similarity, and then the one on the bottom was just to remove names from the cases, just in case that kind of the model started to draw a comparison between names and certain diagnoses, which is not what you would want. Then in terms of the fine-tuning code, so the most difficult part for me was trying to secure GPUs. So I ended up switching to Kaggle. So maybe it's a good segue from the Jeremy Howard presentation, where you get two free GPU T4s for 30 hours per week. Maybe for like, if you haven't heard of those GPUs before, they're about like $2,000 each. But like the best ones that you can use on like Cloud Console that are more expensive are like $25,000 each. So the money was a bit of an issue potentially. Then also maybe another good segue from the previous presentation was I used the Llama 3.23 billion parameter model, instruct model, via Hugging Face. I was fine-tuning that model, and that model you would be able to run locally on a relatively well-powered machine. So that could alleviate concerns about privacy and also give you more control over the technology. And then also, there's a little code snippet down there as well, but also employed two strategies called QLoRa and PEFT in terms of saving the memory use when I was running it in an environment, and also saving time too. Then some considerations if you like to do it for yourself. The token limit, as you saw in those examples, I had it in very small font, but there was a lot of text there. So I had to be careful with how many tokens I was feeding in for the fine tuning, and found a happy medium of 8,192 without overloading the memory at the same time. Also, the loss dropped pretty quick and then stagnated, but I ensured that I kept running it just so that it went over all of the cases, including the rare diseases, which I had towards the back. And the error, I had an error at about 40 per way, so it was like 2 a.m., so I was glad I had the checkpoints saved. And then these are just some more samples of what, like the code. So on the left, that's like the part of the script for fine-tuning the model, and then on the right, that's like generating the new outputs, which was using my model. And then this is some more code for evaluation, which we'll talk more about after. And then for the cost, it ended up costing 16 USD, which is pretty cheap, but theoretically it could cost you nothing if you, by using like an experimental model, which is free, and then also running it. I mean, you'd have to be careful with time constraints, but something like Kaggle, you can get those free GPUs. But then probably a more realistic example is a project called Stanford Alpaca, where they had 50,000 synthetic data examples, and they spent about 600 USD, and I think for me it took about 96 hours to get through like 2,000. They secured the proper GPUs to be able to get through 50,000 in 3 hours. So, and then maybe some envisioned applications for this, because it's local. I was kind of thinking something like automated for clinicians. So like a clinician could have like maybe like a 10-minute or 30-minute like conversation with like an AI and explain like how they like to do things, their kind of personal preferences, and then you could have automated synthetic data based on that like conversation with the clinician, then fine-tune a model, like an already medically tuned model for them, for their personal use potentially. And then also probably a regret, I wish we'd maybe pivoted more towards the rare clinical cases, like maybe just focusing primarily on those rare cases, because I feel like the base model already kind of had quite good knowledge about standard cases, but we'll talk more about evaluation after.
So I'm going to be talking about evaluation now. So Bruno made awesome codes for us to have a really good output. So we have to evaluate which model is better. So we first started off by collecting 87 case reports from BMJ case reports and PubMed, and then we generated outputs using 3 different models, and then we randomized it to see so we can like hide which output is from which category, and then we made an AI evaluator so that we don't have a bias, and then it can strictly follow the evaluation criteria that we've provided. So this is like the 3 different models that we use for the output. The first one is non-fine-tuned llama, so it's just the original llama model that we have right now. The second one is prompted llama, so we gave a very specific and long instruction of what it should do. For example, following the vindicate structure, probable diagnosis, and what steps it should take when doing the clinical reasoning. The third one is fine-tuned llama, so this is what Bruno worked on. So we trained it using 2,700 clinical synthetic data and see what it did. These are some evaluation criteria that we fed into the AI model for it to judge. So we have clinical reasoning, diagnosis, structure, and management for our evaluation criteria. And then going back to the 2 research questions we had, so through the evaluation, we tried to solve the 2 research questions that we had from the very beginning.
Yeah, so in regards to the outcomes, first we compared the fine-tuned llama response with the non-fine-tuned llama, and we used the AI to do that as discussed previously, and we found that 98.9% of the time AI preferred the fine-tuned clinical reasoning compared to the 1.1% from the base model. That's the non-fine-tuned llama. However, in terms of accuracy, we found that the fine-tuned model was only accurate 56.3% of the time, compared to the base model, which was 63.2%. And this is getting the correct diagnosis as per the case report. And so this is just an example of a case that we gave it. So this is the diagnosis was acute subglottic laryngitis as per the case report. So we gave details like history, examination, investigation. This is the clinical reasoning from the base model. So it just provided the diagnosis, no clinical reasoning, no differentials. And this was the clinical reasoning from the fine-tuned model. So it went through differentials, it went through why it was most likely to be this differential or not. And then it gave the final most likely diagnosis. And we also did notice some interesting things. There were a few bizarre outputs with code scripts and duplicate text, and a few other things where the ChatGPT and the fine-tuned models thought that the wrong diagnosis was correct, and a few things like that. So that's something to consider in the future. And then we also compared the 2 models with the prompted llama, and still like the fine-tuned model performed better. And this was just an example of the clinical reasoning from the prompted model. As you can tell, there's more detail, but there is no clinical reasoning in regards to other differentials apart from the primary differential. And so yes, the fine-tuned model was better in terms of clinical reasoning as well as generating the different differential diagnoses. And so we noted that without the prompting, the model did not generate any differential diagnoses or provide clinical reasoning. And without the fine-tuning, the model did not provide any detailed clinical reasoning regarding the different differentials. However, the base model was found to be more accurate in its stated diagnoses. And so in regards to the strengths and limitations of this of our project, so some of the limitations we've discussed, we initially wanted to do 10,000 cases for fine-tuning, but we didn't get too much because of time and the GPUs. We also had to stop the fine-tuning early because of time constraints, so this might have also affected our accuracy. And also in the future, we would consider trying to change the model so that the management options provided would be specific to the Australian context. And also, as shown previously, that there were some limitations with the AI evaluation of the responses. However, some strengths include that this area has not been widely explored until now, and we use high-quality, detailed human seeds to train the model. We also used the combination of the common and more rarer cases, and the AI evaluation allowed us to be less biased as well.
Okay, in terms of future directions, so what we can do in the future. So ideally, we'd like to generate more synthetic data, somewhere around 10,000 and above, and this can help us better assess the model that's been trained on the synthetic data. It would be also helpful to complete the fine-tuning process of the model and see how that affects the results that it produces. And we'd also like to change the evaluation process of the model and see how that changes our results. For example, we'd like to have medical professionals or medical students evaluate the responses from the fine-tuned and the non-fine-tuned model. And we'd also like to compare the performance with other models, so not just the Llama model, but also ChatGPT o1, and see whether the responses are more detailed or less and how that compares. It would also be interesting to diversify the input and output. So instead of just giving the examination and history and the investigations and input, we could ask it for in the output. So for example, just give the history and examination and ask the model to then think of investigations. And that might be useful in the future as well, of reducing the amount of unnecessary tests or investigations that we order. In terms of how we can implicate this into the real world, this could be a very useful clinical aid tool, and it could improve efficiency in patient care as well, just by, I guess, assisting in complex cases and being able to generate that list of differentials. It could also be used in medical education, for example, in simplifying complex cases for medical students, to also have the opportunity to learn from. And as we described earlier, medical data is often, there's concerns of privacy and there's concerns of, I guess, limited data. So using synthetic data can be useful to help train these models to be used in the real world. Yeah. We'd like to acknowledge and thank Clark, Brian, and James for their help in the past few weeks. And thank you. Thank you for listening.